primer lugar, muchas gracias por la invitación y por la presentación y por este magnífico auditorio que casi se me va a quedar pequeño. And in deference to our foreign guests, your foreign guests, I've been asked to speak in English, so that I will now turn into English. Now, as a good theorist, I start by doing some tests of the mechanisms here, which seem to be working. I'm going to talk about Einstein's errors, triumphs, and misconceptions. And the reason why I will insist in misconceptions is that special relativity was invented in 1905 and general relativity in 1916. And in the past decade, we have had so many celebrations about Einstein that he has become some kind of religious saint. And I would like to share with you the information that he was also a human being. Now, let me start by reminding you of what the magnetic dipole moment is, generally symbolized by mu. If you have a circular ring and in it of area A, and you have a particle in it of charge E and mass m moving around the ring at a velocity v, then the magnetic moment, a measure of the magnetism produced by this dipole field, is the current times the area, which I wrote in there, which can be rewritten this way, in which case it becomes E over 2m times the angular momentum, which is mvr. Now, so you expect for this object to have a magnetic dipole moment E over 2m times L. That's the classical result that I presented here. The question is, if you take an electron, which is an elementary particle, is there a factor in front, which is called the zero magnetic ratio, which may or may not be 1. Now, what I have in here is, as a function of the year, various measurements of the zero magnetic ratio of the electron. And you see that one of the first experiments was actually done by Einstein. And as a result, he got that the G was equals to 1, which was his prejudice. Now, later, most experiments went to a result that was G equals 2. That is the prediction of Dirac's theory for an electron which is described simultaneously by special relativity and quantum mechanics, and it happens to be right. And I'm going to tell you something very surprising, which is that both of these results, 1 and 2, were correct at the time. Why am I saying something so peculiar? This is because if you look at the world in which we live, for instance, you look at your gringo neighbors up north, you realize that obviously the world was created at random, otherwise it could not be so bad. And this is actually the case. The world was created at random by a goddess that you may recognize in here as Coatlicue, who happens to have a peculiarity, having to do with the extraordinary and difficult to understand circumstance that the laws that describe nature at a basic level are so absolutely simple and beautiful. So what happens is that the goddess of creation happens to like physics. And on weekends, when she's supposed to be sleeping, she actually reads the physics literature of the week before. And when she reads something like Dirac's theory of the electron, she says, this is so beautiful, it must be true. And since she has all power, she imposes it. So from that day, when Dirac published his theory, the zero magnetic moment of the electron became 2. Now, what Albert Einstein had to say about this is that no one believes in a theory except its author, whereas everyone relies on an experiment except the physicist who conducted it. That's probably adequate at this point. Now, yes. Here we have a photon interacting with an electron. Photon is gamma, the electron is E, with a zero magnetic ratio of G. And the result of Dirac was that this ought to be 2 in value. However, Schwinger, 20 years later, figured out that it's also possible that there is another photon being exchanged between the incoming and outgoing electrons, and then G receives a correction. It becomes 2 plus 1/2 of alpha over pi, alpha being 1 over 137, the square of the electron charge divided by 4 pi. If you go to the next order of perturbation theory, there are 7 diagrams, and to the next order, which is 4th order in the electric charge, there are these 72 diagrams in here. And here's the history of the calculation of the gyromagnetic moment. The physicists like to talk in terms of what they call the anomaly, which is the difference between G and 2. And the anomaly can be calculated as a power series in alpha over pi, which is written in here. And you see the first coefficient was calculated by Schwinger, it's 1/2. The next coefficient by Peterman and Sommerfeld, some 10 years later. The next sorry, these things happen. I have to go back. Come on. Yes. So I am about to tell you about the third coefficient, which was calculated by Laporta and Remedi analytically, is this beautiful formula in here. It's interesting that the observed value of A and the theoretical value are in agreement to 30 parts in 10 to the 12th, and if you convert that into a value of G, it's 30 parts in 10 to the 15. So when particle physicists say that they understand something with precision, they really mean it. This is one example. Now, another interesting thing is that it took 68 years of calculations to do this, so it's not so simple. And last year, something interesting happened. Someone called Stefano Laporta calculated the 891 4th order diagrams in alpha. Analytically, this is the result numerically. He also gave the result to within 1100 digits, just in case you want to check it. Now, the question is, he computed it analytically, but I cannot give the formula analytically because it would take 20 transparencies. SPQB means sono pazzi questi bolognesi. People from Bologna, are they mad? He was at Bologna when he published this. And no, he's not so mad. Never we will have a precision like this one, probably, but you can turn this result around. It is now so precise that by measuring the value of G, you can extract the value of alpha instead of doing the contrary, which is an interesting progress. Next thing I'm going to show you is a formula that probably you have seen more than once, which is this one. And Einstein had the peculiar idea of concluding from his formula that mass increases with energy. This is a misconception of Einstein, who misinterpreted his own theory. If I take C to be 1 units, and this to be the Lorentz factor instead of the velocity in units of the speed of light, then the true value of the energy is gamma times m, and of the momentum is gamma m times v, the velocity, and these two things form a Minkowskian 4 vector whose Minkowskian length is m squared. And that means, among other things, that energy and mass are not the same thing. It's not that mass increases with energy. The mass is fixed. If you're not convinced by that, then you look at excited hydrogen, you let it decay into a ground state of hydrogen and a photon. The energy is conserved in the process, but the mass is not. So a thing that is conserved and a thing that is not conserved cannot be the same thing. Einstein misinterpreted himself. And surprisingly, this is not generally accepted 100 years after special relativity. I made the following experiment. In the Instituto de Física Teórica in Madrid, where I also work, we have a web page where we hang videos answering questions of people who are interested in this or that. So someone asked about this formula, and then I produced a video of 5 minutes length explaining what I just explained in here. And the video was watched by a number of people, incredible number of people, although it's in Spanish, some 50,000 people. And most of the comments were of the type, who is this idiot de Rújula who thinks that Einstein might have been wrong? Now, another thing that you know very well is that general relativity follows from the principle of equivalence. If you are in the middle of nowhere, then you would float in your rocket. And if your rocket is accelerating or is sitting on the Earth, then the acceleration and the gravity are locally equivalent. Why am I going backwards? Apologies, I don't understand these machines. This is obvious. Come on. They wanted me to have my computer inside. Imagine, I would have to go in and out all the time, like a ballet dancer or a... So, acceleration and gravity are locally equivalent. That's the theory, and the question is, how do we know how true that is experimentally? Now, most of you, you're not old enough to have witnessed it, but when the astronauts went to the moon, most people thought, correctly almost, that the moon boot was the only useful application of going to the moon. But that's not quite right, because the astronauts put on the surface of the moon a set of mirrors, very sophisticated, such that a light beam coming to it comes out of it in the same direction. No doubt you can figure out how that works. And pulses of light, laser light have been reflected on the moon for 30 years or 40 years, and we happen to know the orbit of the moon for many, many years with a precision of better than 1 centimeter. And that implies that one can do the following, something called the Northvet test. If this is the Earth, and this is the moon, and this is the sun, then this, following the trajectory of the moon, has as a result that the acceleration difference between the Earth and the moon towards the sun, relative to the overall acceleration, are the same, the two accelerations are the same, to 2 parts in 10 to the minus 13. So the principle of equivalence is at least right to this precision. For a particle physicist, that has a special interest, which is the following. There's a contribution to the mass of the Earth or the moon, which is proportional to Newton's constant, the square of the mass divided by the radius, which is the self-gravitational mass of the object. It's the contribution to the mass by the fact that two pieces of the object interact gravitationally with each other, and that produces a negative contribution to the mass. Now, if you compute it explicitly with the proper density profile and so on for the Earth, this is a 4.6 10 to the minus 10 of the total mass of the Earth is gravitational, and for the moon is about 20 times smaller. And what this implies is the following. I'm drawing these lines as gravitons for the same reason that I would, if I was computing a Coulomb potential, Fourier transform the propagator of the photon, which is this one non-relativistically, to get the 1 over r law. The same thing is true in gravitation if I do it for the one graviton exchange between two pieces of the Earth, then the result is this self-mass. But gravitons have energy and momentum, and therefore they also gravitate. So this piece of the mass of the of the Earth or the moon is also attracted by the sun. And by putting these numbers together, what we learned is that we have been able to measure the triple graviton coupling with a precision of 2 10 to the minus 3, which is about 10 times better than the precision we have for the other non-abelian 3 vector boson coupling, which is that of 3 gluons in quantum chromodynamics. So, on the basis of this principle, Einstein went to his blackboard and wrote this equation in here, which is the equation of general relativity. The left-hand side depends on g mu nu, which is the metric of spacetime, and r mu nu are functions of g mu nu and its 2 first derivatives. And that has to be equal with a factor that contains the speed of light and Newton's constant to a source on the right-hand side of the equation, which is the energy momentum tensor, produced or being had by anything that has energy and momentum. And we shall come back to the point that Einstein, when he thought that the universe was static, added the only term which is compatible with the symmetries of the theory, which is called the cosmological constant lambda times the metric itself, to the right-hand side of this equation. Now, these equations are very well known. In fact, as you can see, they appear even in old trains, and I'm sure you are all thinking that this is Ferromex, but no, you're wrong. Actually, this is in a desert in Bolivia, so not so far after all. Now, the first postdiction of Einstein's theory was the perihelion advance of Mercury, but this very simple equation that I wrote implies the general relativistic model of the solar system that works like a charm, the gravitational wave delay of light signals as they pass close to the sun, the orbits of binary pulsars, the discovery of gravitational waves, the existence and properties of black holes, the standard model of the universe, not only the overall model, but many of its details, and the general relativistic solution to the twin paradox of special relativity, which was, once again, something where Einstein did something that was unnecessary. Now, let me go to the first prediction. That had to do with the fact that if you look at the sun in some direction in the sky, before the sun goes by, in that direction, you see the stars some way. Now, if the sun gets in between, in this direction, you cannot take a picture unless there is an eclipse. And then you see that the stars are not precisely where they should be. And that has to do with the fact that the light carries energy and momentum, and it's therefore reflected by gravity. In this case, the gravity of the sun. If the light goes at a certain distance r, then there is a deflection proportional to 1 over r, which is what you see on the top of this picture. And an interesting result of this was what happened as commentary in the New York Times on November 10th, 1919. They wrote, "Light all askew in the heavens. Men of science more or less agog over results of eclipse observation." Now they couldn't write men of science without getting into real trouble. Einstein theory triumphs. Stars not where they seem to be or where they were calculated to be, but nobody should worry. And by the way, the general relativistic result for this deflection is twice what you would get if you said that the energy of the photon is like a mass and then it's deflected. You would get the result wrong by a factor of 2. Another thing that Einstein did on this field of deviating light by some object on its way was to think of Einstein rings. If you look at something which is precisely in the direction you're looking, hiding something which is behind, then you see what is behind in the form of a perfect ring. It's a perfect lens in that case. In fact, Einstein rings were invented by Schwarzschild some 10 years before Einstein, but they are attributed to Einstein. Einstein, who the only important thing that he said about his rings was wrong. He said that we would never have the alignment and the observational resolution sufficient to see an Einstein ring. And these are 2 counterexamples. Now, there's an interesting counterexample published recently of a cluster of galaxies distorting the light from galaxies behind it, which is this one. And this is interesting anew because it offers a new type of test of general relativity. In the weak field limit, and in the limit of constant curvature, and expressed in terms of conformal time, the equations of general relativity for the metric are what I wrote in here, with the first piece having to do with time, and the second one with the structure of space. And phi in these formulas is the Newtonian potential, and psi is the space curvature potential. And in general relativity, these two things must be identical. But they are not identical in theories that substitute dark matter for a modification of general relativity. So if you prove that y is very close to 1, you are getting information against these theories. And from radio waves going by the sun, we know observationally that y is within a few parts of 10 to the minus 5, close to 1. This other cosmological, very large scale limit does not give such a precise result, only 1% precision, but over much larger scales. So as of less than a year ago, we know that there's a new test of general relativity which is working well. Now I'm going to open a parenthesis here to tell you about something that you know very well, which is the Internet information paradox. The statement is that too much information means the information is no good. Suppose we're going to go now to the debate about clocks. And what do I mean by that? Suppose you Google clock paradox, quote unquote, so that you do not add independent results for clocks and paradox. Then in 0.38 seconds you get more than 700,000 results. That is to say, people are still trying to understand special relativity. And the result is similar if you Google twin paradox. You know very well what the twin paradox is. If I am sitting on this corner when I was young with my twin sister, and in her space I moved from here to there at the relativistic velocity, then when my time is such that I didn't get very old, if I was traveling very fast, she has gotten very old, unlike me. So one of the twins and not the other gets older. And this is interesting because from her point of view, me, who am going away, I'm aging slowly. If I come back towards her, I'm also aging slowly. So when we meet, I'm the younger one. But you could think that from the point of the other guy, me, she is the one who is aging slowly. And when she comes back, she is also aging slowly. So I should be the older one. However, if I follow light signals in every one of her birthdays sent to me, I would see that she is actually aging more slowly than I, except when she turns around. Then when she turns around, apparently she's aging much faster by the right amount to make her older when she comes back. Now Einstein, this is a consequence of the relativity of simultaneity and is not a paradox, I will tell you in a moment, I will remind you in a moment. But Einstein added to this discussion by computing the pseudo-acceleration that he thinks she is having when she turns back, although she is not turning back, he is the one who's moving. And he computed that this pseudo-acceleration was precisely the right one to make him the younger one and not she. Now, that may be a test of general relativity, but it is totally useless because the result of special relativity is that if you are in a given inertial reference frame and you have clocks in it moving at random velocities in random trajectories, then the one clock running fastest is the one whose average v squared along the trajectory is the smallest. And why is the paradox not a paradox? Because there was a MacGuffin, a cheat in presenting the paradox, which is one of the twins is always in one reference system, while the other one changes reference systems. And that little difference is the one that implies that the one that changes reference systems is the one who comes back younger. In spite of this, there has been for 50 years or so the discussion of whether it is the velocity or an acceleration that implies the different pace at which time elapses in the clock of one twin or the other. Everything I've told you now is just theory. But the question is, what does the experiment say about this? And the experiment concludes that accelerations play no role. It's only relative velocities that play a role. This we have known experimentally for a long time, since experiments were done in muons in a storage ring at CERN, decaying into electrons. What you see in here is the number of electrons into which they are decaying. This is a logarithmic scale in time, so this is the exponential decay of the beam of muons. The electrons turn around like this and spit electrons forward, and that's what you see the modulation. The modulation is what measures the magnetic moment of the muon. And the muon is decaying to an electron and a couple of neutrinos. There is now, that was a CERN experiment, there is now one in Fermilab, and they got the result that the magnetic field necessary to accelerate the particles along the track was totally ineffectual in changing the lifetime of the muons. It's only the relative velocities that played a role. That was measured to much better precision by Pound and Repka, who performed an experiment at their laboratory at Harvard by having a source of very precisely determined frequency photons emitted by a Mossbauer transition in iron 57. They dropped them from the top floor to the basement and up to measure how the energy, according to general relativity, increased when going down and decreased when going up. When they finished the experiment, which was done with cold iron, they heated the iron to room temperature in such a way that the iron atoms, iron nuclei, would accelerate by vibrations, thermal vibrations, with a considerable acceleration of 10 to the 16 times the acceleration of gravity that has me standing up here. And they got the result that the effect on the frequencies of acceleration, if there was one, was smaller than 10% that of relative velocities. Now we know this to much better precision, about 10 to the minus 4. So accelerations play no role. All this would be useless for those of you who are studying particle physics, because they will learn how to compute the lifetime of a muon and get the correct result. They will also, if they work a little harder, compute the lifetime of the muon in an external magnetic field, represented here by the wiggly lines, and they will get the same result. So the magnetic field, which is what accelerates the muons in their trajectory, is ineffectual, both experimentally and theoretically. And that closes my parenthesis on clocks. Now you have all heard about GPS satellites. Those are in agreement with general relativity in the sense that at two different places with different gravitational potentials, times flow at different speeds by a factor which is the difference in Newtonian gravitational potential. Weaker gravity means time goes faster. So the satellites correct for this after they were launched, because the first satellites of this type were sent by military people that, unlike the military people of Mexico, which gave me a nice brochure a moment ago, do not understand general relativity. So the first satellites didn't work and had to be corrected by this factor. Now, Einstein himself had many doubts about his thoughts. For instance, he never believed in black holes because he thought that although they were a consequence of his theory, they were too singular to be true. And also another thing he didn't believe on was gravitational waves. Now, is this going to work? Yes. In 1936, Einstein and Nathan Rosen submitted a paper to Physical Review in which they claimed that gravitational waves could not exist in the full theory of general relativity, because any such solution of field equations would have a singularity. The journal sent their manuscript to be refereed by Howard Robertson, who, anonymously of course, reported that the singularities in question were the harmless coordinate singularities of the employed cylindrical coordinates. Einstein, who was unfamiliar with the concept of peer review, angrily withdrew the manuscript, never to publish again in Physical Review. His assistant Leopold Infeld, who had been in contact with Robertson, convinced Einstein that the criticism was correct, and the paper was rewritten with the opposite conclusion and published elsewhere. And Einstein never said that he had been wrong on this subject. Now, why did this turn yellow? Ah, yes, I'm checking whether you are a fast reader. In 1956, Felix Pirani remedied the confusion caused by the use of various coordinate systems by rephrasing the gravitational waves in terms of a manifestly observable Riemann curvature tensor. At the time, this work was ignored because the community was focused on a different question, whether gravitational waves could transmit energy. This matter was settled by a thought experiment proposed by Feynman during the first General Relativity Conference at Chapel Hill in 1957. In short, his argument, known as the sticky bed argument, notes that if one takes a rod with beads on it and a gravitational wave passes by along the rod, the beads would move, friction would produce heat, implying that the passing wave had done work, and therefore it existed. Incidentally, Feynman attended this conference with the name John Smith, because he thought that general relativity people didn't even deserve his presence. So he hid and solved this problem during the conference. Now, this is an object that you have seen, all of you. It's the antenna that used to be in Arecibo in Puerto Rico, a radio antenna. You have all seen it in a film of James Bond, which in this country is called El Ojo Dorado. In Spain it's called El Agente 007 Vuelve, or something like that. Now, these people with such antennas, you can look at pulsars. Pulsars, as you know, are neutron stars rotating and having a magnetic field which, like the one of the Earth, is not aligned with the rotational axis. Those things emit light by a way that we do not quite understand in great detail, but this light, when the beam goes through you, is like a lighthouse. It produces pulses. This is actually an actual picture of a pulsar pulsating. And this is a picture of my estimate of the status of the audience when I am halfway through my lecture. It's also a picture, particularly of Russell House, a student of Joe Taylor. Joe was in Princeton at the time. His student was in Arecibo, very bored looking at pulsar after pulsar, because all the pulsars went, and that was till one day he found a pulsar that went with a separation of about 7 hours between the up and down frequencies. And he immediately realized that he had discovered the first binary pulsar, called 1913 plus 16. I tend to think that this would put a light on the screen, but this type of screen is anti-reflecting. So if I shine a laser, nothing comes out. Now, this system consists of two neutron stars, one which is a pulsar, was a pulsar, because it's changing and it now no longer points to us. And these things move very fast. They get as close as more or less one radius of the sun. The masses of the two things are more or less 1.4 solar masses. The frequency of the pulsar is about 17 times a second, and the common orbit is inclined some 45 degrees relative to the line of sight of the observer. Now with this thing you can immediately measure the period, the eccentricity, and the semi-major axis projected on the plane of the sky, as well as the longitude of periastron, the longitude at which the two things are closest. And those are Keplerian parameters that you can understand without the use of general relativity. And they are measured with some precision. For instance, this is a precision with which the period, 7 and something hours, is measured, quite a high precision. And the data are so gorgeous that you can also measure some post-Keplerian parameters. One is the periastron advance, analogous to the advance of the Mercury perihelion. The other one is a shift of frequency that is partly due to motion and partly due to the gravity of the companion star, and the change of period. The period is increasing as the thing emits gravitational waves, and they get closer and closer, the two objects, because they lose energy by emitting gravitational waves. Now, if I plot in here results in terms of two parameters, the mass of one of the objects, one of the stars, in units of the solar mass, and the same thing for the other, you can see that these three things coincide at a point. So one of the three can be predicted from the other two. By the way, this only works if the emission is of spin 2 waves, like gravitons, which will perhaps never be observed one by one, have spin 2. And this that you have in here is a change of the period with time for 30 years. It changed by 35 seconds in 30 years. And the line is not a fit. The line is the prediction of general relativity. And I think he would have been happy even if he didn't believe in gravitational waves. This would have convinced him. Now these are Halsey and Taylor getting the Nobel Prize in 1993. Halsey is the one with the beard, in case you don't know them. And I am emphasizing this because in the past year we have had so many hundreds of newspapers and televisions, etc., saying that gravitational waves had been discovered. No, they hadn't. They had been discovered so many years earlier. That was the emission of gravitational waves. What was discovered a year and a half ago or so is the arrival of gravitational waves. Now there are pulsars in which you can do this sort of thing with much, much higher precision and check general relativity beyond first order in the strength of the gravitational field. And you can measure that way parameters such as the ratio of the masses measured directly, or S, the sign of the inclination of the orbit relative to the observer. And the yellow region is excluded by the fact that this sign should be bigger than 1. And this very tiny region is where all these very many parameters coincide. And you can, for instance, check the expected, the predicted, and the observed ratio of the deviation of the angle, and that ratio is correct to a couple of parts, or 1 part per thousand or so. So even to second order in gravitation, these theories working beautifully. Now the other thing I told you is that Einstein didn't believe in the black holes either. But you all know by now that if you satisfy this condition between the mass and the radius of an object in units in which the speed of light is 1, if this is greater than 1 and you cross a surface there, it's like something that I read as a child, and maybe you have read, a novel for children, typically horrendous and not worth reading, called El Castillo dirás y no volverás. If you cross this radius called the event horizon, there's no way out. Now, also if a gravitational wave goes through you, or through a ring, it will distort it in this way as it goes by. And once upon a time, 15 million centuries ago, there was a coalescence of two black holes. What you see in here in the background is the effect of lensing. It's not that the stars are moving into one black hole. And that is what was discovered when LIGO discovered gravitational waves. The results, which I'm not going to show, someone else is showing them in this conference, I think, are the most convincing evidence for the existence of black holes. the best test of general relativity in the strong field regime. And more important maybe is that we used to look at the sky with photons, and then from 20 or 30 years ago with neutrinos, we see the neutrinos coming from the sun, for instance. And now we have a third window, which I will call G mu nu for the metric, which is looking at the sky via gravitational waves. Now let me come to the cosmological constant. The cosmological constant, which Einstein considered his biggest error when he learned the results of Hubble, that the universe was not static. In fact, I think his biggest error was to think that the cosmological constant was the biggest error. And the cosmological constant is the energy density of the vacuum, which is an interesting thing even for philosophers. They don't understand it, doesn't matter, it's interesting anyway. Now, what I have in here, sorry if there are any philosophers here, this is, what you have on top is the Hubble plot, that is to say, apparent luminosity distance in megaparsecs as a function of redshift of the light emitted by supernovae of redshifts more than 0.1, that is to say, relatively close by, and they give the same as the same observation as Hubble, that is to say, a linear plot. And from the next one, we will be able to extract the observed average density of the universe in anything that has energy divided by critical density. Critical density in general relativity corresponds to a space-time which is exactly flat. Now, the best fit to these curves that extend to redshift of 2 or so, which is the red line, the dots are averages in intervals of redshift. The best fit tells us from this data that the universe is flat to better than 1%, and that the contributions of the density of the universe are 30% in matter, dark and visible, and 70% in the energy density of the vacuum. So most of the energy of the universe is in the vacuum. Now, this is a picture of an antenna of the Bell Laboratories, and Penzias and Wilson were testing the possibility of reflecting signals from satellites that were called echo satellites, nothing to do with physics. And you can see them here that they were very worried about their antenna because they had a signal that they didn't understand. And in that paper, they referred to that signal as some slimy substances deposited by doves, of which there are a lot in New Haven, where we're doing the experiment. Now, when they cleaned up the antenna, it turned out that they still had a signal, and the signal was coming from the biggest distance at which we can see the universe. And here we have someone coming to our universe and someone going to get out. This is a picture of the microwave background radiation originating in time when the temperature of the universe decreased to a point in its expansion where protons and electrons became hydrogen. And more or less simultaneously, the universe became transparent to light. There was a sudden flash, which is this picture in here, that cosmologists call recombination. They call it recombination because these things have never been combined before, and they always try to confuse you. They also have something called reheating, which is when the universe got hot in spite of the fact that it didn't have to be hot before. Now, what you see in this picture, as you have seen many times, are the irregularities of temperature of this very nice, beautifully thermal light. And the irregularities are at a level of 1 part in 10 to the 5 of the average temperature, which is 2.72 degrees Kelvin. Now, you can look at the amplitude of these oscillations relative to the mean at different points and different sizes. You actually look at the square of the amplitude, And you do that for different sizes of the angular resolution with which you're analyzing your data, and you do this all over the sky, and then you get a result which is a temperature fluctuations in square of microkelvin relative to the angular scale, which you can see here, 1 degree, 2/10 of a degree, etc., etc. And what you see is that there is a fundamental vibration of this object that is emitting the light, and there are harmonics. Now, you all know that if you listen to a note from a musical instrument, you can immediately say, oh, that was, say, a violin. Or if it was a flute, you can say that was a metal flute, or that was a wooden flute, or a clay flute. And the analysis that your ear does of the different harmonics, which is what the strength of the harmonics, that is what drives you to the conclusion of what kind of flute was, is precisely the same thing that is done in here. From the analysis of these harmonics, you can decide what the universe is made of. Not only a flute, but also the universe. And the line here is a fit in a theory, which is the standard theory of the cosmos, called the lambda-cold dark matter. And the people who work in this say that this is a prediction. But it isn't a prediction, it's a 6-parameter fit. And that is obvious from the fact, for instance, that Peebles and Zeldovich published this type of result much before the theory of inflation on which it is now based was born. So we see the average energy densities of the stuff in the universe, they are changing with time. And that was at recombination. This pi tells you that now we are dominated by 3/4 of the energy of the universe is in dark energy. The rest is mainly in dark matter, then a little bit in helium gas, and almost negligible the stars, not to speak of planets or people. Now this is another estimate. This is now 4/5 through the strength of my talk. Now suppose that I empty this room completely. I take the lights out and the air out, everything there is in it out. I also ask you very kindly to get out. Now if I'm left alone here, I will know that the room is not really empty, because if I drop my glasses, they will drop. So there is a substance here that I cannot see, hear, smell, touch, or whatever the fifth sense is that I'm forgetting. Although I cannot sense this object, I know it's here. This gravitational field is permeating this space, even if I cannot perceive it. So I say, let me take this object, there remains the Earth's gravitational field. So I now take the room, which has been completely emptied, I put it in the middle of nowhere, I shield it against neutrinos, I leave nothing, nothing, nothing there in the middle of the universe, and there remains still something that I cannot get out, cannot get rid of, which is the Higgs field. This is another field, analogous to the gravitational field, but with spin 0, which is permeating the universe everywhere, out there and inside you. And this means that the vacuum, which I made, is actually a substance. If the vacuum is a substance, the vacuum is not void, el vacío no es la nada, you can shake it. And the vibrations of the vacuum are elementary particles called the Higgs. Now, philosophers in the audience would have called them to kenonon, because kenon in Old Greek means vacuum. And the LHC, which is the machine with which we discovered this, is not a large hadron collider. It should be an MSV, that is to say, a machine to shake the vacuum. That's what it did. Now here is the machine. It's fairly complicated. I'm not going to explain it. This is an event in which a Higgs was presumably produced, a Higgs particle, and it decays into 2 photons. From the energies of the photons and the momentum of the photons, you can reconstruct the mass of the hypothetical object which decayed in these 2 photons. If you see a signal with a lot of evidence statistically at a certain mass, then you have discovered a particle, in this case, the Higgs. So the vacuum is a substance, meaning that the field, Higgs field in the vacuum, which we called phi 0, is non-zero, and this is actually the mother of all substances. Because, for instance, it gives masses to particles that have mass. Now, there was, many years ago, a contest in Britain to the best way to explain the Higgs field. And someone came up with this explanation, which won the contest, in which Mrs. Thatcher is attracting journalists as she gets into a room. This is the worst possible explanation of the generation of mass. The generation of mass is due to the fact that we know this observationally. The field in the vacuum is non-zero. Then the Lagrangian describing, for instance, the mass of the muon is written in here, in which the coupling of the muon to the vacuum field is the mass, and this is the field itself propagating. So if you have a field propagating in the vacuum, a particle propagating in the vacuum, it interacts with the vacuum expectation value of the Higgs, and that is what generates its mass. If I have a muon and it has a certain energy, given energy, since the muon is rather heavy, it will not travel very fast. If now I have an electron is lighter because it couples less to the vacuum, and it would move faster at the same energy. Now, all these things are not simple words, because one can measure the decay width or rate of a produced Higgs particle into various particles of various masses, which is what is shown in here. Here you have the mass of the particles in GeV versus the coupling to the Higgs field. And the couplings are precisely proportional to mass as the theory demands. So we know that this is true from the top to the muon, which have a mass difference of about 10,000 or something like that. Electrons are not measurable because they couple so little to the Higgs boson that there is no statistics for that. But for instance, the bottom quark, as seen here, has the predicted coupling to the field of the Higgs. Now, once upon a time, the universe presumably was so hot that thermal fluctuations put the value of the Higgs field at zero. But the symmetry of this theory demands that the vacuum expectation value is due to the fact that the potential of interaction of the field of Higgs with itself has a shape like this. And at a certain temperature, the universe fell from here to here. That meant a jump in the value of the self-coupling of the photon, which is the self-energy density of the field. So this is an estimate, this jump is an estimate of what the cosmological constant should be. I'm less than 5 minutes away. It's an estimate of the vacuum energy density of the universe due to our understanding of Higgs physics. And the trouble is that the cosmological constant measured by cosmologists is 56 orders of magnitude smaller than the one resulting from this estimate. Now I put everybody in, Higgs, Gibble, Engel, Guralnick, and Brout, and others. And if you make an estimate based on general relativity, that only mass scale in general relativity is a Newton's constant, then the cosmological constant should be of order 1 over the Newton's constant squared, again in natural units, in which h bar and c are 1. And that implies a disagreement between cosmology and general relativity of 120 orders of magnitude. Now, this is absolutely beautiful, because it's the most gigantic error we have made in the life of science. What could be better? So we see that the standard models of the macro and microcosmos class, like these two drivers in this particular country, and it's the fault of the holes in the ground, it's not the drivers. And so we do not understand the simplest of substances, which is the vacuum. We do not understand gravity as a quantum theory, and we do not understand the relation between gravity and the other fundamental forces. Now, the first guy who attempted to understand a relationship between gravity and electromagnetism, which is something that we still do not understand, was Michael Faraday, the best experimentalist of all times, who did experiments by dropping balls into a cushion and measuring whether the deceleration of the ball when it hit the cushion induced a current in a galvanometer. And he didn't see a result, and being extraordinarily honest, he concluded, "Here end my trials for the present. The results are negative. They do not shake my strong feeling of the existence of a relation between gravity and electricity, though they give no proof that such a relation exists." Now, this is truly honest physics, and it implies that we are still in the same situation so many years after. Einstein's blackboard still has a lot of space to be filled by someone in our next step in understanding, and hopefully that someone would be, for instance, a young Mexican happening to be here in the audience or in the fountain downtown Puebla. And I think this is a good time for me to stop. Thank you.
Thank you very much for this quite interesting talk. So we are starting having questions from the audience. Pueden hacer la pregunta en español si quieren. Aquí la traducimos. Entonces, los chicos que tienen los micrófonos, por favor. Pero antes de iniciar con las preguntas, déjenme comentar que además de esta plática, el profesor Álvaro va a dar una plática el día jueves a las 5 de la tarde como parte de las actividades del Congreso Latinoamericano de Física. Y les aseguro que va a ser igual o inclusive más controversial que esta plática. Entonces, empezamos con las preguntas, por favor.
Hello, I'm Alfredo Sandoval from Universidad Iberoamericana in Mexico City. It's me here.
Okay. Good morning.
So, Steven Weinberg wrote a paper published in the Reviews of Modern Physics pointing this huge discrepancy between particle physics and the cosmological constant value, this 10 to the 100 to 20 or something like that. But that was before the Higgs observation. So my question is,
At the time, Weinberg had a limit on the value of a cosmological constant.
That's right. So the discovery of the Higgs improved, or everything is the same after this discovery regarding this discrepancy? Thank you.
It is difficult, I think, to improve our total ignorance. So I don't think it made any difference. We are equally ignorant. Of course, that doesn't mean that the discovery was not extremely important, but as a problem in micro versus macro physics, it didn't contribute that much. We already knew that we didn't understand anything.
Hay una pregunta hasta allá arriba, por favor.
Allá adelante hay una.
Ahí hay
I want to ask about if the universe expansion isn't affecting the Higgins field.
Say it again, please.
Like if the Higgins field is everywhere in the vacuum,
Yeah.
isn't affected by the expansion of the universe?
That's a very good question, except that it's not the Higgins field, it's the Higgs field. Higgins is the guy playing in My Fair Lady, and my English accent is not good enough to imitate him. Now, of course I forgot the question. Oh yes, ask me again.
The Higgs.
The Higgs field isn't affected by the expansion of the
No,
universe?
it isn't. It isn't.
Okay.
You see, if you have matter, the density of matter decreases like the cube of the expansion factor, because matter is conserved. If you have light, it decreases, the energy density of light decreases like the fourth power, because the frequency of the light is stretched in the same way as the universe is being stretched, as if you draw the wave on a rubber band and expanded it. But the Higgs field has spin zero, and the property of a spin zero field in general relativity is that it is not affected in its energy density by the expansion of the universe. So the cosmological constant, if it is the vacuum expectation value of some scalar field, is not affected by the expansion of the universe.
Thank you.
No, I was going to ask a question, but now it is asked. No, I don't have a further a question, so thank you.
He was going to ask more or less the same question.
Okay, good.
I didn't say, I said that it was a very good question. A very good question is a question of which the speaker knows the answer.
Here you have one more question over there. Here in the front, please.
Does gravity affect Higgs field?
Does gravity affect the Higgs field? No, it doesn't affect its vacuum expectation value. But its vacuum expectation value is an energy density and it affects gravity. So the other way around, yes. Also a Higgs boson has a certain energy and momentum, a particular one, and that affects the structure of space-time the same way as any other object that has energy and momentum.
Thank you.
Okay. Well, there is one more question over there. Yes, please.
Hello, my name is César Ramos from Universidad Nacional Autónoma de Nuevo León.
Sí, sí, te escucho.
Yeah. And, well, I want to know that if the error in the cosmological constant, well, I think that I am asking for your opinion. The error in the cosmological constant, do you think that it has to be with that we don't understand the vacuum, or that we don't understand the interactions between, like you said, Faraday and the electromagnetism and gravity? We don't understand really the relation between that, or even if there is a relation. What do you think that is
I
behind?
don't have an opinion, but I have a hope. I have the hope that when we finally understand a quantum theory of gravity, we will look at the cosmological constant by saying, oh, how could we be so stupid? That's my hope.
Thank you.
Hello, I'm Frank Quintero from Universidad Nacional Autónoma de Mexico. And at the beginning of the talk, you said something about gravitons and how they behaved with the moon and the earth and the sun. From what I have read, I have read that a lot of physicists weren't very sure how these particles behave because of the behavior of quantum physics with gravitation. My question is, how accurate are these predictions that are made with taking into account the existence of gravitons?
About gravitons themselves? Or about gravity coupling to something else? About gravity coupling to something else, we have tests at the level of 1 part in 10 to the 15 or something like that. Well, first of all, I have to say that gravitons, individual gravitons couple so weakly that we have, with current technology, no hope of detecting a single graviton. This is different for photons, for instance. With your eyes, you can detect 2 or 3 photons at a time. Gravitons couple so weakly, individual gravitons couple so weakly that there is currently no hope of seeing individual gravitons. But the one very interesting thing that we know about gravitons, if they exist, is that this, which I drew in here, implies that we understand the coupling of gravitons to gravitons. So if gravitons exist, we know a lot about them, and if they don't exist, we know a lot about their collective aspects.
So even if we can detect gravitons, we can actually be sure that they exist?
Well, one is never sure of something until one experimentally observes it. A single graviton has not been observed and will presumably not be observed for the rest of a century. However, the collective effects of gravitons, you know that light is a wave and it's also an ensemble of particles. And we understand light in both aspects, as a wave and as an ensemble of particles. And the electromagnetic field is also an ensemble of photons. The gravitational field is an ensemble of gravitons, of which we understand the collective effect. Unlike the case of light, in which we can understand both the single particle effects and the collective effects.
Thank you.
Okay, before we close, okay, here we go.
Yeah, I would like to know what is your personal opinion coming from you, that you're an expert in high energy physics and you're in experimental stage. What is your opinion about the string theory and its results? Do you think that it's worth it to keep working on it in order to obtain results, or do you think that it is already done?
Well, string theory is not a theory of nature. It's a mathematical theory until the day it has a prediction which proves some aspect of string theory right. So, as a theory, it's extraordinarily interesting, and it has had a lot of influence on ways to do physics and a lot of influence on mathematics, but at the moment, it's still there out in the sky as a theory of physics. That's an opinion, of course. There are people who are fanatic of string theory. There are manicomios houses that have been full of them. Cuckoo's nests.
Okay, I think we know there are too many questions from this very controversial and very good discussions, but we have to close before we start having lunch here. But I have one last question. Yes. Taking into account that you are working there at CERN as a theoretical physicist, what do you think is the next big discovery, the next big news that CERN is going to announce in a few years, or a few weeks?
If I knew the answer, I would propose that we write, you and I, the article this afternoon. So I don't know the answer. That was not a good question.
Ok, vamos a agradecerle a Álvaro esta plática. Y ahora vamos a pasar a...